All right. Now let me share my screen. All right. Oh, you cannot see me. Why? Oh, I need to start the video. All right. Put it down, but yeah. All right. So today we are going to talk about chapter 6 from the textbook, point location. Okay, so let's go ahead and start. Oh, so before we start, the second assignment is out. So you must have seen the announcement on OttiClass. So it's about finding whether a given polygon, any polygon, is monotone with respect to an arbitrary line. When I say with respect to an arbitrary line, the line is also given as an input to the algorithm. So you will be given a polygon, and an arbitrary line will be also given to you as an input, and so you will be able to devise an algorithm to generically find whether a given polygon is monotone with respect to some given line. All right, so you cannot choose the line by yourself. You cannot write a specific solution for a particular line. For example, you cannot say that, okay, let's do it for x is equal to y line. This is my algorithm. You cannot do that. The line is also going to be given to you as an input. So you need to provide an algorithm to find whether the polygon is monotone with respect to any given arbitrary line. And you're going to provide your algorithm as pseudocode, and you may provide the correctness and complexity analysis of your algorithm as an informal writing. You don't need to have a formal proof of your correctness or the computational complexity. An informal discussion in a paragraph would be sufficient. Okay, so that's for assignment 2. And next week we're going to have the take-home exam, and I updated the course schedule webpage to include the handout time of take-home exam. I plan to give out the take-home exam on December 4th. So we are going to spend our lecture hours next week basically on question and answers. Whether you have any questions, I will be happy to answer on our class next week. All right. And you will have about 2 days to work on the take-home exam. So you will be able to work on the take-home exam over the weekend. So that's the plan. And after that, after the take-home exam, we are going to have 5 chapters to cover from the book, 7, 8, 10, 13, and 15. I gave 2 weeks for Voronoi diagrams, but I think we will be able to finish in 1 week, so we can have one final week off before the final exams start. All right, so that's the plan. We are right at the point of the midterm, middle of the term, at 7th week. And today we're going to talk about a problem, a data structure, which actually is not going to be useful in making the algorithm more efficient in terms of time complexity, but it will be useful to decrease the memory requirements. So we will the data structure we are going to be seeing today. I mean the trapezoidal map. Its main purpose is to decrease the space complexity. So that's going to be something interesting, and it's going to also be a randomized an algorithm, incremental algorithm. The discussion on the proof of the random, the expected space complexity and expected running time is a little bit complex, so I'm going to skip those parts. So I'm just going to indicate the final result directly, knowing that this is a randomized algorithm. I'm just going to describe the main data structure and the algorithm, and I plan to finish all of these in about 1 hour and 15 minutes, so we may skip the break and finish the entire lecture in one shot. All right, so that's the plan for today. So let's go ahead and start. So this is our book. Let me open the book. All right. So yeah, we are right now on chapter 6. Let me directly go there. And the problem, the motivating problem we try to solve, yeah, it's here, is the point location problem. So we are given a map. So we are given a doubly connected edge list. Uh, but in the algorithm that I'm going to describe today, we are going to basically use the edges of that. We will be building the trapezoidal map by just using the edge information of that doubly connected edge list. And a trapezoidal map could be actually uh, constructed by just using line segments. So the algorithm actually describes the line segments are inserted into the map one by one incrementally, and we built this trapezoidal map. But the motivating problem is that these segments actually, they define areas, they define faces, and our goal will be, given a planar subdivision like this, it may be a map, and given a map like this, our goal will be to find which face contains a given query point. So we are going to have queries, point queries, and our goal will be to find which polygon this point is contained in. This is a very practical application, and I remember some graduation project groups had needed such kind of a functionality when they had a mobile application in which they had to find where the user currently is, in which building it is, for example, instead of going over all the building information and making point inclusion tests one by one. That's the brute force. So the query can be answered in ON time, in linear time. But it's possible to do a sublinear query with the help of the data structure I'm going to talk about today. So in such queries, in GIS queries like this one, in database queries, there are three computational complexities that are of concern. One of them is this index structure building time. That's the pre-processing step. Given a map, of course, you need to process all of the polygons to create a data structure that will help you to perform sublinear time queries. But yeah, that's the pre-processing time. The good thing is that we just think about it as a one-time cost. All right, because that if your map does not change dynamically too much, so you don't need to reconstruct your index structure over and over again. So that can be considered as one-time cost. We still don't want to be like, if it's exponential time, if your index creation takes exponential amount of time, again, it may be impossible to create the data structure. So it's still of concern, but if you spend n squared time, n log n time to create the index structure, that one-time pre-processing cost, that's manageable. You can pay that cost. Another thing is that index structure shouldn't take too much space in memory or on disk. So that's the space complexity of your index structure, and the focus of this chapter is to reduce that index structure space requirements. So we will start with the basic technique, which gives O log n. And the third complexity that is of concern to us, of course, is the query complexity. When given a point, finding which of these faces contain this point could be found in O log n time. In the first algorithm that we're going to describe, which doesn't use a complicated data structure, by just using a binary search tree first on the x coordinates of the endpoints. We first figure out where it is. It's like you've tried to figure out where it is in between which vertical lines it lies in. You try to figure out its longitude, and after that, after you find the thin vertical slab that your point is in. So the first search is in the x coordinate like this, and then what happens is that in that vertical slab there will be only line segments that are sorted with respect from bottom to top, and then you perform another binary search on those line segments. These two binary searches, log n plus log n, gives us all log n search time. I'm going to talk about this basic technique first, and then we'll see that such kind of a data structure, if you build binary search trees for every one of those vertical slabs, their total space requirement may be O(n) square. So that's the goal for today's lecture, to reduce that to a better complexity, which is going to have linear expected complexity. We are going to reduce from O(n) square to expected O(n), because it's a randomized algorithm. Its worst case could still be O(n) square, but the expected space requirement will be linear. Okay, so the problem, so we are given a map, polygonal subdivision, we are given a point, and our goal is to figure out which face contains this point. So the first algorithm is the one that uses a lot of space, is this. Given a polygonal subdivision like this, our goal will be, let me copy this to GIMP and work there. All right, so let me move, I need to move it, okay, here, and let me resize a little bit, scale, all right, I think that's sufficient, and flatten my image. All right, so here we are going to be given a query like this, for example. Oops, I'm still moving. Yeah, like this query. We are going to be given a point query, and our goal will be to figure out the face that contains this point. So the data structure first creates vertical extensions from all of the endpoints, all of the edges. We have edges, and edges have endpoints, the vertices. From each of these vertices, we extend towards top and towards bottom an infinite vertical line extended like this, which means that these vertical lines divides, so it's a refinement of the actual subdivision. Actually, we refine the subdivision so that now we have more faces here. If you consider these vertical extension, they provide more faces, but a face is divided into multiple small pieces, but we still label those small pieces with the same face ID. So for example, this large face that this red point is in is refined into 1, 2, 3, 4, 5, 6, 7 smaller pieces, but still they are all labeled with the face ID of this one. Okay, so with this approach, when we have these vertical slabs, when we take a look at a single slab, since we just have these extensions from all of the vertices, if you look at a single vertical slab, it's going to look something like this. Okay, there will be no edge crossings. Edges will not cross each other here. If you look at the line segments that cross from left to right on this vertical slab, we cannot have any vertices inside this, because if there was any vertex here, there would be a vertical extension in that vertex, and we would be looking at a smaller, a thinner slab. Okay, so there will be no vertices inside the slab, and therefore, since it's a planar subdivision, also edges do not intersect each other. If edges intersect each other, we would have a vertex there. We would indicate that intersection point between the edges as another vertex and divide them into half edges as well. So there will be no intersections here, no vertices inside this vertical slab, which tells us that it's possible to order the segments that, or it's possible to order the regions here inside this vertical slab from bottom to top, which will allow us, this sorting will allow us to, I mean, we're actually sorting the segments that cross them. If we sort the segment from bottom to top, there's a total order among them because they do not cross each other. We can also perform binary search on the vertical slab. After you first identify, first you do a binary search on x coordinates, For example, the point is somewhere here. Okay, what we do is we first take a look at this median. We build a binary search tree on these vertical lines, and we check the x coordinate of these vertical lines serves as our key, and we check the x coordinate of the query point. If it's right, we continue our search on the right half. If it's on the left, we continue our search on the left half until we end up at a single vertical slab. And since we're reducing by half each time, we look at the median again. So this may be at the root node, we go right. This may be the right child of the root node, then we go its left. This may be the left child of that. This may be the third step, but in the fourth step, we are going to identify you are in this vertical slab. Since we divide by 2 at each, I mean, this will be like a balanced binary search tree. We will be able to locate this slab, the vertical slab that contains our point. And after that, we will have another binary search tree. For each of these vertical slabs, we are going to build binary search trees on these segments that cross them. So when we have the point, if the point is, if we have that binary search, we are going to now this time check against these segments. Okay, the segments do not have just x and y coordinates, they're complete segments. They will serve as, again, keys at the intermediate nodes, but the question we will be asking this time is this point above or below the segment? If it's below, we're going to continue on one of the halves. If it's above, we're going to continue the other half. And at the end, in this binary search, we're going to locate the face part that contains our point. So the total query time is log n for the first locating the slab, another log n to locate the face within the slab. So in total, it's all log n search time. Now, what is the complexity of this refined subdivision? So that's what's discussed in the book next, which tells us that unfortunately it can be the worst case. It can be O(n) square as this is a worst case example you see on the right. Okay, which has some horizontal slabs and n over 4 horizontal. Actually, yeah, these are, we do not have these vertical slabs. These vertical slabs are not part of the subdivision. The subdivision contains only the vertices of the subdivision are indicated by these large dots. All right, so these large dots are the vertices, and imagine one of these horizontal edges is actually like zigzagged and have some vertices on it. Imagine we have this many like n over 4 vertices that are here, and the other n over 4 are arranged like this. What will happen is that as we extend vertical lines from each of these vertices, we will be introducing a lot of new intersection points with the previous edges. There is no vertex at the original planar subdivision. So while the original planar subdivision's complexity is O(n), there are n vertices and linear edges and faces that are linear on the number of vertices. These vertical extensions may cause a grid-like structure, which is going to increase this complexity to n square. So if you look at how many smaller faces this grid-like structure has, it's going to be n divided by 4 times n divided by 4. So we may have a situation like this. These vertical extensions may create lots of new subfaces, and their number can be quadratic in the number of the vertices. So this is the worst case behavior. But most of the time, if this such a case, I mean, the worst case behavior probably even would not be observed in a general subdivision like this. I mean, it's expected. I mean, worst case is still 1 square, but it's expected as somewhere, I think, on the order of n times square root of n, something like that. But it's more than n log n, so it's still we need to improve on this. So that's the whole chapter is about how can we improve. We had an idea. We had an idea about doing binary search, first on X, then on the segments. We can still use that idea, but how can we reduce this complexity to a smaller one? And the idea is doing these vertical extensions not all the way to infinity, but only to do the extensions until you hit an edge of the original planar subdivision. So what it means is that here we are not going to be dissecting any existing edge. The edges are going to remain intact. We are going to starting from a vertex. We are going to start extending the vertical extension towards top and towards bottom, but we are going to stop as soon as we hit an edge. This is what is called a trapezoidal map. Okay, if you look at this figure, another thing that is different from the previous case is that you see that from this planar subdivision looks like the previous planar subdivision, but there is some differences actually, and that difference is that in this new case, in order to tell the algorithm in a better way, I mean, in order for the algorithm to work correctly, actually, we are going to need the points to be in general position, which means that no two vertices should have the same x coordinate. All right, so it's going to, if you compare these two figures, let me copy it here. Okay, if you look at these two, and you'll notice the difference. These two vertices, they had the same x coordinate previously. Now the bottom one is a little bit to the right. So this new subdivision is modified a little bit so that the modification is now no two vertices have the same x coordinate. So that's what we have here. All right, no two vertices have the same x coordinate. With that, we'll be able to identify each of the trapezoid with four constant information. We're just going to be storing four things about the trapezoid here. And if you look at the shapes that are inside this trapezoidal subdivision, you'll see that they are either triangles, and triangles are like degenerate trapezoids in which one of the left or right vertical extensions is actually a single point. All right, they are all of them are quadrilaterals. If you look at, so this is a better view. When it's shrinking down, it becomes, some of the lines are not visible that much. So if you look at this, all of them are trapezoids, meaning that they have two parallel sides, and those parallel sides are going to be our vertical extensions. And it has a unique top and bottom edge. Each of these parts here, they have unique top and bottom edges. And by the way, given we actually bound the unbounded face with a rectangle. So before we start the algorithm, we use a bounding box, a rectangle, to bound the entire region in a rectangle, and therefore all of them will have a unique. All of the regions here, they have a unique top and bottom edges. They will also have some left and right points which could be identified. Each one of them will have a right or left point. This right and left point could be either something like this. The left point of that will be an edge, may actually and here in the vertical extension on the left hand side could contain a vertical extension that starts at a vertex like this. Okay, we may have something like this if we have independent line segments. It's possible, or even if they're not independent, we can have a situation image. Imagine there are two other line segments that goes towards like this. We can have an extension that will cause a trapezoid to have a vertex in the middle of an edge like of the vertical extension on the left hand side. The right point could either be at it may belong to the bottom edge, it may belong to a top edge, or again it may have some another point that ends at the vertical extension like this. But if you look at it, so these are the different cases. So here, another case, the right point is actually on another edge. But what we will store for each trapezoid, we can identify them uniquely. We are going to store only 4 bits of information, 4 types of information for every trapezoid. A trapezoid will be indicated by its top edge. We are going to store the edge at its top. We're going to store the edge at its bounding it at the bottom. We are going to store its left point and right point. Okay, so these are the things that we're going to store with left point, right point. So left P, right P, top and bottom. So we are going to store two edges and two vertices for each trapezoid. And the book discusses different cases where the left point can be a single, it may not belong to an edge. There may be no vertical extension on the left point. It may be the beginning point of the top edge. It may be the beginning point of the bottom edge, or it may be the end point of some third party, a third edge that ends at this vertical extension. But the thing here, the main thing here is that the trapezoidal map is going to contain, and we can identify trapezoids only by using a little amount of information for each of them. All of them are trapezoids. They're uniform. Even those degenerate trapezoids, which are like triangles, they also have these 4 bits of information. And if you look at this, we will not have this worst case O(n) square complexity because we're not dissecting the existing edges. We're not going to be introducing quadratic number of edges in this trapezoidal map. But such a trapezoidal map, okay, you have these vertical extensions. Now, how do you conduct? There are no vertical slabs anymore. There is no vertical slab that goes on all the way. So this trapezoidal map is a little bit complicated than the first data structure. We need a search structure. What kind of a search structure we can use on this map so that we can still perform queries in log n time? If you look at this, okay, at certain points, for example, if this line here goes all the way until here, we have a point here. I cannot compare my point here with this line because this line doesn't exist here. The vertical slabs do not partition the entire region into these x-coordinate bounded regions. I cannot directly perform queries on the vertical slabs. They do not continue all around. And the edges too, the sides too, they also do not continue all the way around. The edges are not divided. Some of them are long, some of them are short. So we have this problem, but we can solve that. We are going to see a data structure which actually can still make binary search queries, queries similar to binary search by building a nice data structure on top of a trapezoidal map. And our algorithm, I'm going to show you a randomized incremental algorithm, which will create the trapezoidal map and the search structure together with it. So the trapezoidal map is what you see here. It's that's doubly connected edge list with these vertical extensions. So that's the trapezoidal map. But the search structure is something else. We need to create some kind of a binary search tree. What should be the inner nodes? What should be the leaf nodes? That search structure should also help us to answer point location queries. Okay. Interestingly, that search structure we are going to have is not going to be a tree. It's going to be a directed acyclic graph, and the reason is that we will still be using vertices of this map. The vertices will be used as keys, as intermediate nodes that will help us to locate our point to the left or right subtrees. Okay, so each point here is going to divide the tree and each intermediate node is going to be dividing into roughly half the remaining entities. So it's going to be a binary tree. And we are going to, at these vertices, if we come to an intermediate node that is a vertex, we will be asking the question, is the query point to the right of this point or to the left of this point? And we are going to continue the search on the part that of the search structure that is to the right. But if you look at this, certain faces, like this one right below this vertex, part of it is to the left, part of it is to the right. You look at this, there's a single face here. This part is to the left at this point, this part is to the right of this point. That's the reason actually why this is not going to be a tree, but a directed acyclic graph. What will happen is that we will have multiple leaf nodes that represent actually a single leaf node. There will be a single leaf node for every one of those trapezoids, but what will happen is that it will be possible to come to the same leaf node from the right branch and also from the left branch. If the query is, for example, here to the left of this vertex, we will be following the left branch in that directed acyclic graph, and we will still end up at the same trapezoid. And sometimes we will be able to follow the right branch. If the query point is here, we are going to follow the right branch and arrive at the same trapezoid. So if you have alternative paths from the root node that arrives at the same leaf node, it cannot be a tree. In a tree, there's a unique path from any root from the root node to any leaf node. So this tells us it's not going to be a tree, but it will have vertices to guide our search, and it will also have these segments, these line segments that are here, the original segments, the original edges of the given planar subdivision, input planar subdivision. They will also guide us in our search to answer queries like, is the query point above or below the segment? Based on that, we are going to again continue either on the left branch or the right branch. So there will be, the intermediate nodes will be two types. It will be just like in KD trees, we were looking at x coordinate, y coordinate alternatingly. This is not going to be on an alternating manner. It's like these two types of nodes are going to be all over the place in the tree, but segment type intermediate nodes will help us to locate the query at above or below that segment, and point-like intermediate nodes are going to answer queries, is it to the left or right, or whether our query point is to the left or right of this given data structure. So it's the trapezoidal map. Let me just show you a glimpse of how it's going to look like for an example. Yeah, it's going to look like this. So this figure here, let me zoom in. This figure that you see on the PDF shows a trapezoidal map built for two line segments. As I said, since we are going to treat each of the edges of our planar subdivision separately, we are going to process the edges to build this trapezoidal map. What we have here is an example which shows our planar subdivision actually has a single face. Actually, I mean, it may, in terms of the point location query, this example doesn't make any sense because this is similar to the third question in your first assignment, right? If that condition holds, you can only have line segments in the planar subdivision, and there will be only one unique unbounded face. It's the same thing here, right? I mean, we have a single unbounded face if this is the planar subdivision. So it doesn't make sense to actually answer point location queries. Our answer will always be the same. We will always be saying that it's located in this unbounded face. But just for the sake of a simple example, imagine there are multiple faces, and these two segments. I mean, imagine we do not see the other parts of the actual input graph. It may be. This is just to show how, for given line segments, how we can create a trapezoidal map and the corresponding search structure. In the book, this tau is called, I mean, this T is the trapezoidal map, and D, this D here it refers to the search structure that we are going to build simultaneously during the randomized incremental algorithm. So what we are going to be doing is that we are going to be inserting these one by one. Right now we are seeing a finished search structure for these two line segments. As you can see, the vertical extensions from P1, P2, Q1, Q2, we have these vertical extensions from all of the vertices. And they divide the entire region into trapezoids, and there are no degenerate trapezoids here. All of them are trapezoids. A rectangle is a specific case of a trapezoid in which top and bottom also happens to be parallel to each other. So their left and right boundaries are always parallel to each other, so that makes them a trapezoid. This is the top, this is the bottom. For example, for the trapezoid D, the 4 bits of information we are using is this. Its top is S1, its bottom is S2, its left point is P2, its right point is Q1. So that's what we store for trapezoid D. Top is S1, bottom is S2, left is P2, right point is Q1. So those are the information we are going to store for. This is the information we are going to store for every one of those trapezoids. And if you look at the search structure, you'll see that every one of those trapezoids you see here, they appear as leaf nodes, and the segments and the points, they appear as intermediate nodes. So when we have a point here inside F, okay, right, assume this mouse pointer, this hand is the query point. We're first going to compare it against P1. It's to the right of P1, so we are going to continue the search on the right. Then we are going to compare it against Q1. So that's the next node we have. It's to the left of Q1. So we are going to continue here. We are going to check S1. Is it above or below? If it was above, we are going to end up at trapezoid B, and that's where it would be. But it's below S1, so we continue on the right. And then we look at P2. On the right of S1, there are two parts, C and this DF. And we go to the right of P2. Again, we check with S2 against S2. There are again two parts. If we were above S2, we would be in trapezoid D, but we are below S2, and which will lead us to this trapezoid F. As you can see, it's possible to come to trapezoid F by following the route to the left of Q1 or to the right of Q1. So based on this our result on Q1, we could have arrived F1. If the query point was to the right of Q1, we should still be able to arrive at F because that's where the point is. But even if it's to the left of Q1, again, this query is still in F. So there are two routes that ends up at F in this tree. So it's not a search tree, but it's a graph, a directed acyclic graph but still, if it's height, it will have a height starting with it because it's a directed acyclic graph. It has a root node. We can topologically sort all these. So there are levels of the depth of a node is well defined. Its distance from root. We can use the minimum or the maximum of these, since the distance from the root can be two things, as in this case. So the depth can be identified as the maximum of those two distances from the root node. And if the maximum depth, if the maximum depth of a certain node is on the order of log n, it means that this will be like a balanced tree, and it will provide the number of steps that we will take is going to be on the order of log n if we can do that. And the expected complexity expected complexity of the query will be log n. And all right, so this is the search structure that we're after. And let me see whether I'm missing anything. There are certain lemmas in the book, which the first part before the algorithm, the first part discusses this trapezoidal map itself. We have shown it like this, but we haven't yet proved that it's not O(n) square. What is the complexity of such a trapezoidal map? And the first lemma, actually, the first lemma tells that everything in here is a trapezoid. So the first lemma is about its name. It's called a trapezoidal map because each face here, in general, if it's in general position, meaning that no two vertices have the same x coordinate, we will have a case that there will be only this 4 bits of information will be sufficient. This constraint of no two vertices having the same x coordinate is important, because if we don't have that, we may have cases that are like this. Look at this trapezoid delta. Its left is just crowding with lots of trapezoids. There are 5 trapezoids. There is no single left point. And it's all because we have x coordinates that are that are the same. So we have to get rid of these cases so that our trapezoidal map works. And the way we are going to get rid of this is with what we call shear transform. We are going to transform each of the vertices of the initial planar subdivision before we built the trapezoidal map, such that based on the y coordinates, we are going to translate the x coordinates. We are going to increment the x coordinate of every point with an amount proportional to its y coordinate, which means that since if two points have the same x coordinate and also have the same y coordinate, it means that they are the same point, right? I mean, we don't have such cases, as two distinct points cannot have both the x coordinates and the y coordinates equal to each other. So the ones with x coordinates equal to each other should have their y coordinates different. So if I add some value proportional to their y coordinate, it means that their x coordinates after this addition, their x coordinates will no longer be the same. So that's the shear transform we are going to apply. We are going to like tilt the entire image a little bit towards right, but the ones at the bottom, they're not going to be tilted that much. The tilting is going to be done more at the top vertices. But while we are doing this, we don't want to destroy the topology, original topology of the face, for example. Especially what we don't want is, we don't want the ordering of these vertices, whether it's left, right, the ordering of these vertices from left to right, we don't want it to change. So we don't want to move it too much. Our goal in this sub-problem is, given vertices that are like this, given the vertex positions, the points, find an epsilon in such a way that if you have this, the new axis, yeah, let me flatten the image. In this, what I'm going to do is, I'm going to change the x coordinates of all of these vertices. What I'm going to do is, I'm going to add an epsilon amount of, I'm going to multiply their y coordinates with epsilon, and I'm going to add this to their previous x coordinates to get this new x coordinate. Find an epsilon as small as possible, or what is the largest epsilon that's not going to destroy the original ordering of the points. If you have, if they're ordered x1, x2, x3, x4 from left to right originally, if this is the original order of your vertices, based on their y coordinates, this shear transform, if this epsilon is large enough, it may switch their positions, right? I mean, if x4's y coordinate is much higher than x4, it may be possible that when you order them with x prime, their order is going to change. We don't want that. Without changing the original permutation of the vertices, what is the maximum epsilon that you can apply on this subdivision? So that's a sub problem that you may try to solve, and actually it's solved in one of the sections, but I'm going to skip that part. So just know that it's possible to just get rid of this constraint. I mean, that says, given the points are in general position, no two vertices will have the same x coordinate. And with that information, our trapezoids, this lemma is going to be true. Every face in this new subdivision will have only one point on their left, only one side, like this one trapezoid, or at most two trapezoids. They will be bottom trapezoid. I mean, as you can see on the left side, there are two trapezoids of this one, but its neighboring left and right neighbor trapezoids can be four at most. So this is what this lemma 6.1 says, and by using this lemma, actually the next lemma 6.2 proves that a trapezoidal map has linear complexity. A trapezoidal map of a set of n line segments in general position, and this general position means that no two vertices have the same x coordinate. That's what they mean by general position. And it contains at most 6m plus 4 vertices and at most 3m plus 1 trapezoids. So this is the part that says the trapezoidal map has a linear, an exact worst case linear complexity. That's the trapezoidal map. What about the search structure? The search structure could still be have more complexity, even if because there are many intermediate nodes. Same segment can be used as multiple intermediate nodes. We had that, right? If you remember the figure in this randomized incremental algorithm, S2, the segment S2 is used twice as intermediate node. Okay, so that may be possible. So the intermediate nodes may be duplicated. This brings us to question, what is the complexity of the search structure then? And in the randomized algorithm, we'll see that the expected complexity of the search structure will also be linear. All right, so now I think we're ready to talk about the construction of the search structure algorithm. Yeah, we are at that point. Okay, now the algorithm is this. Actually, I can describe it from the slides as well. So we have also the slides somewhere here. Let me open them too. So the good thing about this Andy Mirzayan slides is that it talks about the historical development of the problem as well. So the problem is one of the classical problems in computational geometry. It has many applications in geographic information systems mainly, but in other areas too, for example, mobile telecommunication, mobile robotics. Whenever you want to locate something in an environment, these algorithms may be used. So we have talked about these, and yeah, here's the historical part. So there was a one-dimensional version of this, which is given a point query, can you identify which interval contains your point? You can answer this with binary search easily. And the binary search, actually, the search structure shouldn't be n log n. The search structure still should be O(n) if you're just doing a sorted array. If you have a sorted array, why does the, oh no, sorry, this is not the T is not the time to do the search structure. It's the time to the pre-processing time to build the search structure. So sorting a given number of arbitrary points takes n log n time. So that's the pre-processing time. Building the index structure takes n log n time. The index structure itself is linear. It's just assorted points, and finding where your query is located between which two points takes log n time with just binary search. That's a very common algorithm, and as you can see, it's not attributed to anyone. It's very simple. The binary search technique is the very simple algorithm. And the 2D version, the first method, the slab method, the infinite vertical extensions that we have seen at the beginning of the chapter, it's due to Shamos, and he developed it in 1975. And as we have seen, the space complexity is n square. And the pre-processing time also can take n square time. Therefore, since the space that we are creating is O(n) square. But the search is still log n. So that's interesting. We're not trying to improve we already have log n search. We're not trying to improve that in this chapter. Our chapter the algorithm is Seidel's algorithm, the randomized incremental method. It was proposed in 1990, 30 years ago. This algorithm, the search structure was proposed, and its expected complexity is linear. The expected running time is n log n, this incremental method, and it will provide an expected search time of log n. We will create a search structure with expected log n height at the end. And there are other algorithms that are following these. Actually, they're before in 1983. So this Seidel's algorithm is this expected algorithm is like optimal. So that's why we are going to describe it. So we have seen the slab methods, the Shamos methods, and the randomized incremental method. We see that we are not extending the vertical extensions all the way to infinity. We stop when we hit an edge, and we have talked about this. Every trapezoid can be identified by 4 things: left, right point, top, and bottom. And here is the randomized incremental. So this is the same search structure that is given as an example in the book. And here is the algorithm. Okay, the algorithm is actually not that difficult. The difficult part is updating the search structure, and each case is handled separately, but we don't need to. The examples that the book gives shows that it's not so difficult to arrange the new nodes, insert new intermediate nodes into the tree. I'm going to show two examples here, but the algorithm itself is very simple. We start with an empty trapezoidal map, empty search structure. And since this is the randomized algorithm, what we want is we first want to randomly shuffle our edges, our line segments that are given to us, because a certain order of them may lead to a worst case running time, also worst case search structure. So we don't want that. So we just want to insert them in some random order. So that's second step 2. We randomly permit them. And I mean, all of these randomized algorithms, what makes them random is just this random shuffling. But you see the important point in randomized algorithms is their analysis. If I have this random permutation, what is the expected height of the tree? What is the expected time to construct this tree is what is difficult. Okay, and as I said, for this one, it's a rather bit complicated, so I'm going to skip that part. So I'm just going to describe the algorithm, and then we'll be done. So by the way, so I'm not going to have a break, so it's already break time, but I'm going to finish in about like 10-15 minutes. All right, so we will be finishing early today. So the algorithm is this. For every one of those line segments, we are going to insert them one by one incrementally, and we are going to update both the trapezoidal map and the search structure. And the trapezoidal map and the search structure will be correct for the first k inserted segments. When you're inserting the kth segment for S1 to Sk minus 1, the trapezoidal map is the correct trapezoidal map. So, and we will be actually using them here when we're inserting segment Sk. So let Pk and Qk be the left and right endpoints of segment Sk. What we do is we find the trapezoid that Pk is in. We call it delta 0, that trapezoid. So since we have a search structure at this moment, what I do is this Pk is like a point query. The left end of this line segment is a point query. I perform this point query in log n time, okay, in expected log n time. This step here is going to take expected log n time, and I will find this delta 0, the trapezoid that this first endpoint, the trapezoid that contains the first endpoint. And what I will do is, my goal is only the trapezoids that are intersected by the entire line segment is going to be affected, both in the trapezoidal map and in the search structure. The other parts, the parts of the trapezoidal map or the search structure that are not intersected by our new line segment that we are currently inserting, they are not going to be affected at all. So our goal is to find all the trapezoids that this line segment intersects. And for that, in the book, there is a separate function. Actually, it's embedded here. This while loop that you see here is actually written as follow segment. A separate procedure is given for this. So let me, in this incremental algorithm, show the trapezoidal map. If you look at the pseudocode, it's just lots of English words. We just have a for loop that says insert every segment one by one. First, find this set of segments intersected by your new segment. Remove those trapezoids because they're going to be affected, means that they're all going to have to divide it into smaller trapezoids. So the original trapezoids that are intersected by our segment, they have to be removed. Those leaf nodes are going to be removed from our trapezoid. And we are going to add, so these leaves are removed, and we are going to add new sets of trapezoids and with intermediate nodes. So this, everything is done in step 6 actually. It's just described as an English sentence, how to modify the search structure, and the trapezoidal map is described in English in step 6. And it's just, we are going to see with some examples, with 2 examples, how we will get the new search structure and the trapezoidal map. So this step 4 is actually is done by using this algorithm named follow segment. So given this segment SI here, our goal is to find delta 0, delta 1, delta 2, and delta 3. Okay, we don't want this trapezoid is not going to be affected. All right, so the way we do that is this: we find delta 0, and then we just the while loop. If you look at the while loop, it's very simple actually. This follow segment. If the second endpoint, we locate P in the search structure, and until we reach Q, we continue walking along the trapezoids by looking at their right points. So if Q lies to the right point of the current trapezoid, it means that there are still more trapezoids to intersect, and we continue. So this line here says that if there are more trapezoids to intersect, we haven't reached the end point yet. So this right point P, every trapezoid had 4 bits of information. We are using one of them here, the right point of a trapezoid, which gives actually the x-coordinate of this right point tells us whether we have reached our destination in terms of this following when we're following our segment. So, and then what we're going to do is we're going to also not going to use only this x-coordinate. This right point, if it's right point, we are going to check whether it's above or below SI. Just as in this example, if you look at this example, the right point of delta 1 is this, and we are going to compare it against SI because based on that, we are going to follow this segment or this segment. In order to continue with delta 2, I need to know that my segment is below or below this right point, or right point is above this segment SI. If it was vice versa, if this segment was somewhere here, this right point will be below. It would be below this SI, and what I'm going to do is I'm going to follow this segment. So this if condition here is actually trying to distinguish between two cases where it's either this delta 2 or this whatever unnamed trapezoid here. Either we are going to follow here or here. Okay, it's possible to follow because delta 1 may have potentially a trapezoid has potentially 2 neighboring trapezoids. So to uniquely follow these trapezoids from left to right, we check its right point against the segment that we're inserting. And based on that, we are either going to continue with the lower or upper right neighbor, and that's it. This while loop is going to continue all the way until we reach the end point. And we are going to, with that, we will be identifying the set of trapezoids that are intersected by SI. And the rest is just modifying the search structure. If we know this trapezoid, we are going to have an extension from the left endpoint to the top of delta 0 and to the bottom of delta 0. And from Q, we have the last trapezoid that is intersected. Again, we are going to use its top and bottom to modify the trapezoidal map. And how do we modify the search structure? Let's look at the examples on the slide. So we just update, and everything we do again here is indicated by with one line: update the trapezoidal map and the search structure accordingly. Here some examples are provided on the next slides. This is the simplest case where the segment is contained entirely in a single trapezoid. If we have a single trapezoid that we intersect, it's really easy actually. That single trapezoid is going to be replaced by a structure like this, which is going to contain the both endpoints as intermediate nodes and also the segment itself. So it's going to divide a single line segment like this is going to divide the trapezoid into 4 new trapezoids. The one to the left of P, the one to the right of D, and the one above. And the part that is in between P and Q are going to be separated into 2 trapezoids as below and above the segment. So hence we have these 4 trapezoids. This SK is used to distinguish between B and C. P and Q are used to distinguish between A and D, as you can see, like this. Okay, it's like it becomes like a decision tree type of thing that we insert. We just insert in total 7 new nodes. 4 of them leaf nodes, 3 of them intermediate nodes for a single trapezoid. The general case actually is not going to be that different because we will be doing a similar thing for the first and last trapezoid. We will be adding 3 new trapezoids for each of them, and for the trapezoids that are in the middle, they're just going to be separated by the segment as above and below. So we can still have some general function. Okay, so this one shows. Now, if our segment intersects 4 trapezoids from delta 0 to delta 3, delta 0, delta 1, delta 2, delta 3, how are we going to update the search structure? How are we going to update the trapezoidal map? First of all, these 4 leaf nodes, they're going to be deleted. Let's delete all of them. Now, how many new trapezoids are going to be introduced? As you can see, again, to the left of PK and to the right of QK, again, we have single trapezoids that are there with the same top and bottom of the previous one. The left point of the previous trapezoid, delta 0, is still the left of A. So it's not, if you think about this, writing the code for this is not going to be that difficult. We are going to reuse the information we have about delta 0. And the only information I have about delta 0 is its left pointer, left point, right point, top edge, bottom edge. So its left edge, left point is going to be the left point of A. Top and bottom doesn't change. And what I do is PK is going to be the right point of this A. So now I have correctly identified a new trapezoid at leaf node with left point, top, bottom sharing delta 0 and its right point becoming PK. And as you can see at the rightmost node here in this search structure, we have QK, and to the right of QK, we have again the same thing, this new trapezoid G, which is going to be sharing the bottom and top of the last trapezoid that is intersected. Its right point will be still the right point of G, and its left point will be QK. So we just solved how to insert these new leaf nodes A and G. And if you look at what happens in the middle, is all about the segment itself. Some of them are going to be above, some of them are going to be below, and the information that we store in delta 1, delta 2, for example, the top edge of delta 1 is going to be the top edge of C, okay? And on the other hand, for the trapezoids that are below SK, their top edge will be SK. And whatever bottom edge they have, whatever delta 1 had as the bottom edge, we are going to store that information at B and D. So, and as I said, all the other trapezoids between PK and QK, we will distinguish, separate them with the help of the segment itself, whether they're above or below these trapezoids. We are going to update the records accordingly. And this becomes, actually, this is like a very generic case. If you write the code to make the modification of these 4 trapezoids, it will be very similar. If it's 5 trapezoids or 6 trapezoids, what you're doing for the trapezoids in between are going to be very similar, a very generic code that you will be doing. Okay, so this is how we modify the search structure, and that's it. The complexity is with expected log n complexity. As I said, I'm skipping that randomized probabilistic analysis of the expected complexity of the search structure and the query time, but their expected size of the search structure is linear. The construction time, the expected time is n log n, and the expected query time is O log n. So it's very efficient. If you randomly insert these nodes into your tree, you will be able to answer these queries very fast in a very short amount, storage space. And I talked about this shear transform, and this slide actually indicates better. So what our goal is to modify, to transform these original points into these new points without modifying their y coordinate, but slightly incrementing their x coordinates. So the effect is going to be like this. But the figure in the book did not have this. Actually, it was like more like x minus epsilon ay. So you could also have that. You can modify the x coordinate either by incrementing them or decrementing them. what I remember from the figure, which is in GIMP, as you can see, they had the same x coordinate. The one at the bottom is more to the right, right? I mean, look at these two vertices, V1 and V2. V2 is now to the right of V1, which means that we did not actually perform this x plus. I mean, if this is the positive y coordinate, if this is the positive x coordinate, and this transformation that we see here is more like x minus epsilon y. Looking at these 2 points, maybe if you look at other points, maybe it may be something else. Let's see, are there other? So yeah, look at these two ones. This one here and this one here. Yeah, considering these two, actually the one above is a little bit to the right. So this figure that is drawn in the book is just drawn inconsistently. Actually, they just dragged the vertices, the ones that are below, they just drag them randomly so that no two vertices have the same x coordinates. So the figure that you see here is not the result of a shear transform, a consistent shear transform, because if it was like that, we would see a consistent shift towards right for the vertices that are at higher y coordinates. Okay, but you get the idea. It basically says that it's possible to get rid of this constraint where no two vertices have the same x coordinate. All right, and that's it. So if you don't have any questions, that's it for this week. And we're going to spend the entire next week's lecture for question and answers. So if you can study to the previous chapters and this one, and meanwhile, before the Wednesday's lecture next week, I will be happy to answer your questions. Okay, so that's it for today. See you all next week. Don't forget to submit your assignments, second assignment. I think it was due this Sunday, or it should be something like that. I gave you like about 10 days. It shouldn't be so difficult to try to figure out some algorithm for this monotonicity problem. But yeah, don't forget to submit your assignments, and see you all on Wednesday next week. All right, bye. Take care. I'll stop the recording.